Hello everyone, this is Mr. Molikash again. This is our week 5 video for Math 172. This week you'll be looking at what are called the trigonometric identities, and I've put this this sheet that I'm about to show you in the week 5 folder in Blackboard. The book talks about, in section 5.1, about the fundamental identities, and it calls this first set, instead of tangent identities, it calls them quotient identities, and the reason for that is because tangent and cotangent are both quotients of sine and cosine. One's the reciprocal of the other. But the book calls those quotient identities. So this is in 5.1. The reciprocal identities are also fundamental. They're in 5.1. Pythagorean identities are in 5.1. Even and odd identities, that's important to know. I'll talk more about that in just a moment, about why they're even and odd. But you should keep this sheet handy when you're working on homework and in ALEKS. Maybe have it open in a different tab. Or just print it out like I did. You'll need this entire sheet at some point in this course, with the exception of down here, the law of tangents. You won't need the law of tangents for this class. And you'll also, I'll put optional down here. You also won't need to use Mollweed's formula, although you can use Mollweed's formula to check whether you've solved the triangle correctly, and we'll get into that in chapter 6. So I'll just give you a moment here to look at these identities and consider all of them. Some of them, are just basic definitions, like, but as we'll see in just a moment, these words, tangent, cotangent, secant, and so forth, they actually have a root meaning, and the words are used also in geometry. So this all has to do with the circle in geometry. So let's just draw a circle real quickly. Okay, a tangent line is a line that just intersects a circle in one point. If you put the circle on the grid on the x and y plane, and you let this point be 1, 0, then this is the, what kind of circle? Unit circle. Very good. Alright, so this is the x-axis and this is the y-axis. And we could draw several different triangles having to do with this circle. So let's say that central angle theta is drawn in the first quadrant, and this length would be this cosine of theta. This is the sine of theta, and of course this is 1. So just by the Pythagorean theorem, we know that a squared plus b squared equals c squared, and of course 1 times 1 is itself, right? So another triangle we could draw is this one. So we could draw, and I'm going to have to go through where I've labeled something, but if we draw the tangent from this point out to where it meets the x-axis, we know from geometry that the tangent is perpendicular to the radius at this point of tangency. So this would also be a right angle, and this is a right angle. Okay, well, oddly enough, this segment outside of this triangle is called the tangent of theta. And if you divide this length and this length, you get this length. Amazing, right? Another length that's a segment or line or ray that intersects a circle, where the line could intersect in more than one place, for example the x-axis, is called the secant line. So this length from here all the way through to here is called the secant of theta. And believe it or not, the secant is the reciprocal of the cosine. We could do some simple math to show that in just a moment. So, but you can see the Pythagorean theorem holds true for this triangle, right? 1 squared plus tangent squared equals secant squared. All right, so you may not realize why, tangent and secant are related to these sides. So let's separate and redraw these two triangles. So here's the first one that has cosine theta, sine theta, and 1. And then what I'm going to do is I'm going to take this this other triangle. I'll draw this in red right next to it. And these are called similar triangles, and the reason for that is because well, this angle theta is now right here. Right? If we kind of rotate this, flip it over, turn it around, the right angle would be here, the theta would be here, and then this other angle is this same one right here, right? So the short leg of this triangle is 1, right? So, let's call these other sides, for example, B and C from the Pythagorean theorem. So, we know from similar triangles that B is the sine theta as 1 is the cosine theta, right? And so if we solve for B, we get sine theta over cosine theta, which we know is tangent theta, right? From our previous identity sheet, right? Tangent is sine over cosine. So, so B, therefore, is the tangent of theta. Okay, let me move this over just a little bit, so hopefully I'm still on the camera. Okay, we also know that C is to 1. The hypotenuse is the hypotenuse, as short leg is the short leg, right? Well, what is C divided by 1? It's just C, right? And 1 over cosine theta, according to our definitions, is secant theta. Okay, so that's the reason why, that's the reason why those are called what they are, right? Tangent is actually a length that's tangent to the unit circle, and secant is a length that's secant to the circle. And you'll learn more about secant lines and tangent lines when you take Calculus 1. Maybe you'll take that next semester or next year, Math 271. Okay, there's a third triangle real quickly, and I won't spend too much time on this one, but there's one that you can draw up here where this length is the cosecant of theta, and this is the cotangent of theta, and it comes alongside the tangent. And so the third one here would be cotangent squared plus 1 squared equals cosecant squared. So there you go. That's kind of what's going on there. So those are, just a little bit of a demonstration as to the identities involved there. So what we're going to have to is use these identities in different problems. So I'll go look at some examples from the textbook. So one of them says to rewrite this expression. With no fractions. Simplify this, write the final form with no fractions. So one strategy is to take every function that's not sine or cosine and then rewrite it so that it's in terms of sine and cosine. So we know from our identity sheet that tangent x is sine x over cosine x. And this is cosine x times itself, right? Okay, and then the secant is the reciprocal of the cosine, so that's 1 divided by the cosine. Okay, and then we can see some things canceling out, right? So this and this go away. As long as cosine is not 0, this is well defined. So as long as we're not doing 0 divided by 0, we're good. But Same thing here, right? So the only thing that's left over is the sine of x. So that's the simplified form of what's up here, is just simply sine of x. So working with trig functions using these fundamental identities, that's kind of what we need to be able to do, is use the fundamental identities to simplify, more complicated expression. Okay. Okay. So we'll say that's example 1. Okay. So these get a little bit more complicated, obviously. So here's another example, and I may have to, finish this over here on the right. But the second one is to try to simplify this: cosine over sine plus sine over 1 plus cosine. And let me go ahead and mention while we're doing this that the way that I do this problem is not going to be the only way that it can be done. There are, if you see another way of doing it and you wind up with a similar or mathematically correct answer, that's fine. But what I would like to do with this is to find a common denominator. The only way that we can add 2 fractions, and it says write the final form with no fractions. So the only way to simplify this is first we're going to add the fractions, and then hopefully some stuff will cancel out like we had above. So what I'm going to have to do is take this fraction and multiply it by this factor over here. So that's 1 plus cosine theta over itself, right? And then the second fraction, I'm going to have to multiply it by sine theta over itself. And by doing that, you can see that both denominators are exactly the same. Okay, so I can put that stuff in the denominator. Okay, now we're going to have to work out the numerator. So we have cosine theta times 1 plus cosine theta times itself plus sine theta times itself. Okay, and remember from our fundamental identities from the previous page that whenever we see these things added together, that's exactly 1, right? Well, look what I see. Ta-da! That's exactly 1. So move this up a little bit. You get cosine theta, which is this cosine theta, right, plus 1. And the reason I turn this around backwards, you don't have to do that, but the reason I'm turning it around backwards is to show you that that same exact thing is in the denominator, right? So all this divided by all this is 1, right? Is 1. And 1 divided by sine theta is cosecant theta. So that would be the simplified form of this big, ugly stuff that was written in black before I put the red and the green there. Okay, so yeah, these are just a couple examples of simplifying. Another objective you have to do is to verify an identity that's already been put into effect, right? So, let's look at one of those. So, oh, by the way, I can't put this on the screen right now, but there in section 5.1, there are guidelines for verifying a trigonometric identity. I highly recommend that you read those and you follow those in the steps, in the order that they are written. I'll just quickly mention them. One is work on one side of the equation, keep the other side in mind as your final goal. Number 2 is to do what we just did in the last 2 examples, to use the fundamental identities to simplify something. And then 3 is to apply basic algebraic techniques such as factoring, adding fractions with a common denominator, etc. And then if all else fails, we could just rewrite everything in terms of sine and cosine. Remember, that's what we did in our first example, right? Everything got written in terms of sine and cosine. So, all right, here's an example of verifying an identity. And so there's just one of these that we'll have time for in this video. And I've put some other videos in this folder for you. Sorry, that's code tangent. I've put some other videos from Patrick JMT in this folder so you can look at some further examples. And also, don't forget that in the textbook, there's videos before. Just about every example in the book has a video to help you understand why things are working out the way that they are. All right, so 3, we want to verify this identity, right? So we want to show that all this stuff really does equal 1. All right, well, looking at our guidelines here, like, we're going to try to work with a more complicated side and get that simplified so that it equals 1. Another thing we should point out here is that when an angle is a negative sign, like negative x or the opposite of x, we're going to use these even odd identities. And the reason for them being called even odd identities is, and I'll just mention this and then come back, because we're going to have to use those identities, right? So the reason why we're going to do that is because the definition of an even function is if f of x and f of negative x are exactly the same. There are 2 even functions that are trig functions. One is cosine x, so it's equal to its opposite, and then secant, it's reciprocal. Okay. All right, so those are even functions. And then the odd functions say, all right, f of x and f of negative x are not equal, but they're exact opposites of each other. They're exact opposites of each other. So if you change the angle to its opposite, then the value that you get from doing that is an opposite sign. All right, so that's all the rest of them, right? So sine of x, the opposite of that, is the same thing as the sine of the opposite of x. Okay, so these are called odd functions, and its reciprocal honors the same thing, as does tangent and cotangent. Okay, so I'm just writing down, you don't have to write this down, but, and it's reciprocal. I'm just writing this down to explain why they're called even and odd. But just kind of keep in mind that all this stuff is already written here on this page, right? So you can see they're all written there. All right, so without any further ado, we're going to rewrite this in terms of sine x. Okay, that's use the odd identity. Cotangent is also odd, so that's going to be negative cotangent x over cosine x. All right, and right now I'm going to say, okay, does this equal 1? All right, now I'm not sure yet because I'm trying to verify this. I haven't really proved that it equals 1 yet. So for now, I'll put a little question mark there, but we're going to quickly find out that this really does work. First off, a negative times a negative is a positive, and sine over cosine is cotangent. I'm sorry, is tangent, my fault. Tangent, right? Well, now we want to see, okay, does that really equal, and by the way, this is cotangent over 1, right? So just cotangent. But anyway, if you go back and remember the tangent identities, tangent is sine over cosine. What's cotangent? Well, that is cosine over sine. These are exact reciprocals of each other, right? So if you didn't know that it equals 1 at this stage, you know, you could apply the final guideline and just rewrite everything in terms of sines and cosines, and then you'll see that everything cancels out and you get 1. So it verifies. Okay, that's really all we have time for right now. But I do again encourage you to print this out and use it. Also, if you have any questions, concerns, comments, complaints, you know, send me an email, or if you think it's appropriate for the whole class, put it in the Ask Mr. Molikash discussion board. Thanks so much.